Hello, my name is Roy Simpson, and I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This is another video in my Proofs in Differential Calculus series. In this video, we are going to go ahead and prove that the derivative of x is just equal to 1. So this is a very quick proof. And as I mentioned in a previous video when I proved that the derivative of a constant was 0, it's better to view these proofs geometrically first. Now, as you can see, I went ahead and graphed on here the line y equals x, the slope of which is just 1. You can see that rise over run is just going to be 1 here. So I go up 1 when I run 1. And so that means that the slope anywhere on this line is going to be 1, which is exactly what the derivative function represents. The derivative function represents the slope of a function at any given point, the slope of the tangent line of the function at any given point. But since this is a line, the slope of it is constant. The prerequisite knowledge that I assume you have going into this, you have to kind of know quite a bit about limits, and specifically the limit definition of a derivative. Or perhaps, as it should be called, the true definition of a derivative. So let's hop into this proof. We'll go ahead and start with the statement. We're going to go ahead and let our function equal x itself. And then we happen to know that by the limit definition of a derivative, that f prime of x should equal the limit as h approaches 0. So as our little wiggle approaches nothing, of f of x plus h minus f of x. And again, all over h. This just basically means that x and x plus h are kind of approaching each other. In fact, x plus h is approaching x. And so you have a difference in y over a difference in input. In fact, that's such an important statement that I'll take the time out here just to kind of draw it out. You have a point x and another point x plus h. So that h is just a little wiggle. And so that point x leads to an output of f evaluated at x. That point x plus h leads to an output evaluated of the function evaluated at x plus h. And you know that the slope of the line containing these 2 points is f of x plus h minus f of x, which is exactly what this numerator is, divided by the difference in the x values, which is x plus h minus x. Well, x plus h minus x is just h, and that's what the denominator is. So that was a little bit of a diatribe, an aside there. Sorry about that, but it's good to see that. So let's finish out the proof because there's not much else to it. This is equal to the limit as h approaches 0 of, when I plug x plus h into our function, I get x plus h. When I plug x into our function, I get x. This is all over h. And as you see, this becomes the limit as h approaches 0 of h over h, which cancels nicely, is now the limit as h approaches 0 of 1. And of course, since that no longer depends upon h, that limit actually is 1. That is the entire proof, not much else to it. Hope you enjoyed it.